Welcome to today's paper reading. Today's paper is titled, SpQR, a Sparse-Quantized Representation for Near-Lossless LLM Weight Compression. This paper was published on AR14 by Tim Dettmers and colleagues from University of Washington, HSE University, Yandex, IST Austria, ETH Zurich, Skoltech, and Neuromagic. The abstract highlights recent advancements in large language model, LLM, pretraining, resulting in high-quality LLMs with impressive capabilities. These models, when compressed via quantization to 3 to 4 bits per parameter, can fit into memory-limited devices like laptops and mobile phones, enabling personalized use. However, this level of quantization often leads to moderate to high accuracy losses, particularly for smaller models in the 1 to 10 billion parameter range, which are ideal for edge deployments. To tackle this accuracy issue, the authors introduced the Sparse-Quantized Representation, SpQR, a new compression format and quantization technique that enables near-lossless compression of LLMs across various scales, achieving similar compression levels to previous methods. SpQR works by identifying and isolating outlier weights that cause significant quantization errors, storing them in higher precision, while compressing other weights to 3 to 4 bits. This results in relative accuracy losses of less than 1% in perplexity for highly accurate Llama and Falcon LLMs, making it possible to run a 33 billion parameter LLM on a single 24 GB consumer GPU without performance degradation and with a 15% speedup, thus making powerful LLMs accessible to consumers without any downsides. SpQR also includes efficient algorithms for encoding weights into its format and decoding them efficiently at runtime, providing faster inference than 16-bit baselines at similar accuracy, and enabling memory compression gains of more than 4x. The Sparse-Quantized Representations, SpQR, is a novel approach designed to compress large language models, LLMs, to 3 to 4 bits per parameter while maintaining near-lossless performance. This hybrid format combines two key innovations: isolating outlier weights that would otherwise cause disproportionate errors if quantized, and implementing a variant of group quantization with small group sizes. The process of converting a pre-trained LLM into SpQR format involves an extended version of post-training quantization, which includes an outlier detection step to identify weights with significant impact on layer output behavior, followed by an efficient compression step that compresses most weights to low bit width while preserving the model's predictive performance. Figure 1 presents the performance of compressed large language models, LLMs, for Llama models. On the left, it shows the language model, LM, loss on the Wikitext2 dataset against the model size. On the right, it displays the average performance on zero-shot tasks against the model size. The figure highlights that SpQR achieves superior performance compared to GPTQ and RTN at similar model sizes, especially for smaller models. This improvement is attributed to SpQR's ability to achieve higher compression rates while minimizing loss degradation. Additionally, the figure indicates that SpQR, with 4.6 to 4.71 bits per parameter, approaches the performance of non-quantized models with a maximum margin of error of 1% for all models, as detailed in Table 1. The focus of this section is on post-training quantization, PTQ, methods, which are widely used for model compression. These methods are particularly effective for vision models and small-scale language models with fewer than 100 million parameters. However, as models grow larger, such as GPT-scale models, the computational and memory costs associated with these methods become prohibitive. Recent advancements have introduced methods like ZeroQuant, LLM.int8, and NuQMM, which use direct rounding of weights and customize quantization granularity to manage these challenges. Table 1 presents a comparison of perplexity scores on the Wikitext2, C4, and Penn Tree Bank datasets for SpQR, RTN, and GPTQ baselines with Llama models. The data shows that SpQR achieves perplexity scores within 1% of the 16-bit models while using less than 4.71 bits per parameter. Notably, SpQR demonstrates significant improvements over GPTQ at 4 bits per parameter, with the improvement being as large as the gap between RTN and GPTQ. This indicates that SpQR is an effective method for compressing large language models while maintaining high performance. The sensitivity of weights in a neural network to quantization is not uniform. A weight is considered sensitive if its rounding error is significant, which can be amplified by large inputs. However, modern quantization algorithms exploit correlations between weights, allowing errors in one weight to be compensated by adjustments in another. This requires a robust definition of sensitivity. For computational efficiency, sensitivity is assessed at the layer level using calibration inputs. The sensitivity of a weight is defined as the minimum square difference between original predictions and those with the weight quantized. This problem allows for a closed-form solution, leveraging the optimal brain surgeon framework. Figure 2 presents a detailed analysis of the weight log sensitivities from the last attention layer of the Llama 65B model. The visualization uses dark blue shades to indicate higher sensitivity. The left image provides a high-level overview, resized to a 1/32 scale with max pooling applied. The middle images are zoomed-in views from the main figure, while the right images are from other weight matrices. Key observations include the presence of row outliers, which exhibit high sensitivity across entire rows or partial regions. Column outliers are also identified, showing high sensitivity in specific input dimensions. Additionally, a repeating pattern of sensitivity every 64 units, attributed to rotary embeddings, is highlighted. The SpQR algorithm introduces a sensitivity-aware approach to quantization, which differentiates between low and high sensitivity weights. This approach aims to allocate more of the representation size budget to sensitive weights, which are often critical for maintaining model accuracy. To achieve this, SpQR employs bilevel quantization, where small groups of weights, typically between 8 to 32 weights, are quantized separately with their own scale and zero point. This method runs contrary to current intuitions, but is justified by the need to capture the sensitivity of these small groups. Additionally, SpQR identifies and handles high sensitivity outliers by keeping them in high precision, 16-bit, and encoding them in a compressed sparse row, CSR, format, which significantly reduces the overall quantization error. Figure 3 provides a high-level overview of the SpQR representation for a single-weight tensor. On the right side of the image, all stored data types and their dimensions are depicted. This figure is crucial for understanding the structure and components of the SpQR representation, which is designed to efficiently compress and store weight tensors in a manner that maintains high precision and performance. The overview highlights the various data structures and their sizes, which are essential for implementing and leveraging the sparse-quantized representation effectively. Figure 4 illustrates the different types of outliers in the Llama 65B model. The figure highlights that unstructured outliers significantly reduce perplexity more quickly compared to row outliers and the criterion proposed by Dettmers et al., DZ22. This effectiveness is observed even when accounting for differences in memory footprint. The analysis underscores the importance of treating outliers in a manner that captures their unstructured nature to achieve better model performance. The experimental setup focuses on three key settings: determining the most compact representation for SpQR to replicate 16-bit model performance, controlling the average number of bits per parameter, and finding the best trade-off between model size and performance. The evaluation involves Llama and Falcon models, comparing SpQR against GPTQ and round to nearest, RTN, quantization baselines. Metrics used include perplexity on datasets like Wikitext2, C4, and Penn Treebank, and zero-shot accuracy on tasks such as Winogrande and PyQA. The main results show that SpQR significantly outperforms GPTQ, achieving near-lossless compression and substantial performance improvements, especially on smaller models. Table 2 presents the perplexity results on Wikitext2, C4, and Penn Treebank datasets for the Falcon model, comparing SpQR with round to nearest, RTN, and GPTQ baselines. The data shows that SpQR achieves performance within 1% of the perplexity of the uncompressed model, using less than 4.5 bits per parameter. Notably, for 4-bit quantization, SpQR demonstrates a significant improvement over GPTQ, with the improvement being as large as the improvement from RTN to GPTQ. This highlights the effectiveness of SpQR in maintaining model performance while reducing the number of bits per parameter. Table 3 presents the perplexity results for the Llama 65B model across different configurations. The uncompressed model shows perplexities of 3.53, 3.74, and 3.75 on Wiki2, C4, and PTB respectively. The GPTQ model with 4 bits per parameter has perplexities of 5.62, 5.73, and 5.76. The 3-bit statistics configuration, with a group size of 16, achieves perplexities of 3.63 across all datasets. This table highlights the performance differences when using different quantization methods and bit depths. Table 4 presents a comparison of inference speeds in tokens per second, tokens/s, for different models, with a focus on the SpQR algorithm's performance. The table highlights that the optimized SpQR algorithm achieves significant speedups, being faster than the 16-bit baseline and nearly 2.0 times faster than the combination of quantized matrix multiplication and standard PyTorch sparse matrix multiplication. Notably, OM indicates that certain models did not fit within the memory capacity of an A100 GPU, underscoring the importance of efficient algorithms like SpQR for handling large-scale models within constrained hardware environments. The SpQR quantization approach achieves near-lossless 16-bit accuracy with an average of less than 4.75 bits per parameter. It also offers an improved quality size trade-off when compressed to as little as 3.36 bits, making it suitable for memory-limited devices. However, the evaluation is limited to predictive performance metrics such as zero-shot accuracy and perplexity, without assessing generative quality. The authors hypothesize a strong correlation between perplexity and generation quality, which they plan to investigate in future work. Additionally, while a sparse matrix multiplication algorithm is devised for computational acceleration, it is not fused with regular quantized matrix multiplication, which could further enhance inference time performance. The implementation of such a fusion is considered challenging and is left for future research. The authors acknowledge the support from multiple funding sources. Dmitry Kuzmin was supported by the Russian Science Foundation under Grant 21-11-00373. Dmitry Alistarh and Elias Frantar received funding from the European Research Council under the Horizon 2020 Research and Innovation Program, specifically Grant Agreement number 805223 Scale ML. Additionally, the authors expressed their gratitude to Ivan Komarov for his assistance in profiling and understanding the performance bottlenecks of SpQR on GPU. In this section, we delve into additional visualizations of Llama weight sensitivities, focusing on 4 main factors: the quantization scheme, layer depth, the role of the weight, and its location within the weight matrix. We compare 2 GPTQ 3-bit configurations, one using Perot quantization scales and the other using blockwise quantization with a block size of 128. This comparison helps illustrate how the group size affects sensitivity, particularly in terms of quantization error. Additionally, we explore the impact of rotary embeddings, noting a regular pattern of sensitivity that repeats every 64 rows, which we attribute to the implementation of rotary position embeddings in Llama. Figure 5 illustrates the weight sensitivities for the Llama 65B model's 40th layer, specifically focusing on the attention query projection. The figure is divided into 2 parts, each representing a different quantization scheme. The top part shows the sensitivity using 3-bit GPTQ with Perot quantization scales, while the bottom part uses 3-bit GPTQ with a block size of 128. The color scale in both parts is logarithmic, with darker shades indicating higher sensitivity. This visualization helps in understanding how different quantization schemes affect the sensitivity of weights within the model, particularly highlighting the impact of block size on quantization error. Figure 6 presents the weight log sensitivities for a deeper upward projection layer, specifically layer number 79. The heat map on the left visually represents the sensitivity of each weight, with darker colors indicating higher sensitivity. The histogram on the right provides a detailed view of the sensitivities in the first 100 and last 100 columns, sorted across input dimensions, This figure clearly demonstrates that later columns exhibit higher sensitivity on average, highlighting a significant trend in the model's deeper layers. Figure 7 illustrates the mean quantization error on the vertical axis as it varies with layer depth on the horizontal axis. Each plot within the figure corresponds to a distinct role that a layer can play within the model architecture. This visualization helps in understanding how quantization error is distributed across different types of layers as the depth of the model increases. In this section, we introduce the key hyperparameters used in the SpQR representations. These include the number of bits per weight, BW, bits per scale, BS, and bits per zero, BZ. Additionally, we define the outlier rate, RO, which is the fraction of weights that are not quantized, and the block sizes for weight, beta 1, and statistic, beta 2, quantization. The outlier threshold, tau, is crucial for managing outliers, and it is tuned within the range of 0.1 to 1.0 using a binary search method with a minimum step size of 0.05. In this analysis, the performance of the SpQR algorithm is examined in relation to the choice of quantization group sizes. The algorithm employs two types of groups, indexed by parameters beta 1 and beta 2. The beta 1 group dimension encompasses multiple weights for the same input unit, akin to standard blockwise quantization. Conversely, the beta 2 dimension covers multiple output units and is utilized when quantizing quantization scales. In the visualizations, beta 1 blocks are consistently horizontal, whereas beta 2 blocks are vertical. The study quantizes the Llama 65B model using 3-bit SpQR for both weights and statistics, and evaluates perplexity on the Wikitext2, Penn Treebank, and C4 datasets. The results are presented in Table 5, where the upper left section displays the effective number of bits for each group configuration, and the subsequent sections report perplexities across the different datasets. This setup allows for an assessment of how varying the quantization group sizes impacts the overall performance of the SpQR algorithm. Table 5 evaluates the performance of SpQR with varying parameters beta 1 and beta 2, quantizing Llama 65B with 3-bit SpQR for weights and statistics. The table reports perplexity on Wikitext2, Penn Treebank, and C4 datasets. The upper left section contains the effective number of bits for each group configuration, and the remaining sections correspond to perplexities on different datasets. The uncompressed baseline values are provided in the corresponding headings. To estimate the compressed model size, we use the average bits per parameter, which is calculated as the total model size in bits divided by the number of parameters. The model size in bits includes the memory required for quantized weights, first-order and second-order quantization statistics, outliers, and the outlier index. According to Section 4.2, each outlier requires approximately 32 bits of memory, which significantly impacts the total memory requirements. The optimal configuration for fixed average number of bits involves several key factors. Firstly, smaller groups of bits can significantly enhance model performance, especially when the fraction of outliers is kept between 0.2% to 0.5%. However, the benefits of adding more bits diminish as the additional budget from small groups is relatively small, typically around 0.1 to 0.5 bits per parameter. It is generally more effective to store weights in higher precision rather than using lower precision with very small groups or a large fraction of outliers. In the experiments conducted, the optimal fraction of outliers varied depending on the specific model and group size. The results also showed that the SpQR method, which uses less than 4.3 bits per parameter, achieves performance within 1% of the perplexity compared to the GPTQ method, demonstrating a significant improvement over both RTN and GPTQ baselines. Figure 8 illustrates the relationship between perplexity on the Wikitext2 dataset and the average number of bits used in quantization configurations. Various markers are used to denote different bit widths, BW. The black colors represent quantization configurations without outliers, and the brightness of the color indicates the outlier rate, with brighter colors corresponding to higher outlier rates. This figure helps in understanding how different quantization settings impact model performance, as measured by perplexity. Table 6 presents a comparison of perplexity scores on the Wikitext2 C4 and Penn Treebank datasets for the SpQR method and two baselines, round to nearest, RTN, and GPTQ, using the OPT model. The data indicates that SpQR achieves perplexity levels within 1% of the baselines while using less than 4.3 bits per parameter. Notably, at 4 bits per parameter, SpQR demonstrates a significant improvement over GPTQ, comparable to the improvements seen when moving from RTN to GPTQ. This table highlights the efficiency and effectiveness of the SpQR method in near-lossless compression scenarios. This section presents additional results for near-lossless compression. The quantization configurations for OPT are detailed in Table 6 across three datasets: Wikitext2, Penn Treebank, and C4. Furthermore, results from the LM evaluation harness for Llama are reported in Table 7. The recently released Falcon models, specifically Falcon 7B and Falcon 40B, are also included in Table 8. Table 7 presents the evaluation results of Llama models using the LM eval harness. The models evaluated include Llama 7B, 13B, 30B, and 65B. The evaluation metrics cover various aspects such as Winogrand, Pika, Heliswag, Arc-Easy, and Arc-Challenge. The table also highlights different compression methods applied, namely SpQR, RTN, and GPTQ. These results provide a comprehensive view of the performance and efficiency of the Llama models under different compression techniques. Table 8 presents the evaluation results of the Falcon models, specifically Falcon 7B and Falcon 40B, using the LM eval harness. The table includes metrics such as average bits and perplexity, which are crucial for understanding the model's efficiency and performance. Additionally, the performance of these models is assessed across various benchmarks including Winogrand, Pika, Heliswag, Arc-Easy, and Arc-Challenge. This comprehensive evaluation provides insights into the capabilities and limitations of the Falcon models in different scenarios. For optimal large language model, LLM, configuration on specific hardware, consider the memory constraints of the device. For instance, an iPhone 13 with 4 GB of memory should use the 7B Llama model with a compression level of less than or equal to 3.5 bits. On the other hand, a high-end GPU like the RTX 4090 with 24 GB of memory can handle the 65B Llama model with a compression level of is asymptotically equal to 4.5 bits. The A6000 with 48 GB of memory also recommends the 65B model at is asymptotically equal to 4.5 bits. These recommendations ensure that the model fits within the device's memory without requiring offloading of parameters and activations. Table 9 illustrates the optimal selection of Llama models based on various memory constraints across different devices. The devices listed include iPhone 13, iPhone 14, consumer laptops, and high-end workstation GPUs like RTX 4070, RTX 4080, RTX 4090, V100, and A6000. The memory capacities range from 4 GB for mobile devices to 48 GB for high-end GPUs. The Llama models considered are 7B, 13B, 30B, and 65B. The table provides specific memory constraints for each model, indicating the best fit for different device memory budgets. This selection is crucial for deploying models without the need for offloading parameters and activations, ensuring efficient use of device memory. To ensure the robustness of our results, we conducted experiments using multiple random seeds. Specifically, we ran SpQR with 5 different random seeds ranging from 0 to 5 and measured the adjusted standard deviation. The compression parameters used were BW equals BZ equals BS equals 3 and Beta 1 equals Beta 2 equals 16, resulting in 3.625 bits per parameter. The perplexity scores obtained were 3.75 plus or minus 0.003 for Wikitext2, 7.03 plus or minus 0.01 for Penn Treebank, and 5.75 plus or minus 0.00086 for C4. These standard deviations are significantly smaller than the differences observed between SpQR, GPTQ, and RTN, indicating that our results are robust to random seed variation. In this section, we present examples demonstrating the effects of SpQR quantization on text generation. We evaluated the original Llama 65B model against two quantized versions, SpQR and RTN 4-bit. Specifically, we employed the SpQR configuration that achieves near-lossless compression. All generated samples were produced using greedy autoregressive inference to ensure reproducibility. The examples show that while all models generate valid text, SpQR more frequently matches the quality of the 16-bit model. Additionally, the near-lossless SpQR algorithm tends to produce text that is more semantically similar to the original. Figure 9 presents the text generated by various quantized Llama 65B models when given the same prompt. This comparison highlights the differences in output among the models, which is crucial for understanding the impact of quantization on text generation quality. Each model's response to the prompt is displayed, allowing for a direct assessment of how quantization affects the coherence, relevance, and creativity of the generated text. The deployment of SpQR enables high-quality large language models, LLMs, in the 7 to 13 billion parameters range to be run on memory-limited devices like laptops and phones. This is achieved by developing specialized 7 billion parameter LLMs in 16-bit precision and then deploying them to phones using SpQR, which is practically lossless. This ensures reliable performance for consumer applications. Ethically, LLMs are dual-use technologies that can bring both benefits and harm. However, the impact of SpQR is expected to be positive or neutral as it does not create new capabilities but rather makes existing models more accessible. Figure 10 presents a grid of weight log sensitivities for the Llama 65B model under 3-bit GPTQ compression. The grid includes per-row quantization statistics, with each row corresponding to a specific layer type such as attention query or MLP gate, and the columns representing the layer depth. This visualization aids in understanding the sensitivity of weights across different layers and types within the model, providing insights into the effectiveness of the compression technique. Figure 11 presents a grid of weight log sensitivities for the Llama 65B model under 3-bit GPTQ compression with group-wise quantization of block size 128. The grid is organized such that each row corresponds to a specific layer type, including attention query and MLP gate, while the columns represent the layer depth. This visualization aids in understanding the sensitivity of weights across different layers and depths, providing insights into the effectiveness of the quantization method for maintaining model performance. In this paper, the authors utilized two large language models, ChatGPT and Claude+, to assist in various aspects of the research. These models were employed to expedite the writing of LaTeX code, specifically in Algorithm 1 and Figure 3, which was created using TIX. Additionally, the LLMs were used to enhance the design of tables throughout the document. Beyond these tasks, ChatGPT was used to generate prompts for Appendix I, while Claude+ was utilized to formulate the outlier criterion in Algorithm 1. All interactions with the LLMs were conducted through chat-based interfaces, allowing for iterative refinement of the generated code and suggestions. Thank you for watching.